Swayam Prabha. Digital India. Educated India.
Good morning, I am Dr. N. K. Samadhya, Associate Professor in the Department of Civil Engineering, IIT Roorkee, and I am going to deliver a lecture on shallow foundations today. As you know that all the engineering structures are supported by soil and rock, and those not, they either fly, float or fall over. So, you will find that in all the cases of all the civil engineering structures like dams, buildings and multi-storied buildings naturally, and all type of civil engineering structures, whatever it may be a road or a railway embankment or any other thing, they are supported by a proper foundation. Now, when we say proper foundation, foundation means it is the lowest part of a superstructure and which normally exists below the earth surface. Now, it refers to the material whose behavior the civil engineer has analyzed in order to provide satisfactory and economical support to the structure. Now, these foundations may be classified at different type of foundations, and these foundations, as we know that they are below the earth surface, then they are out of sight. So, although out of sight, the foundation is nonetheless important, because if it is deficient in design or construction, the entire building or the superstructure is at risk. And you can take that Leaning Tower of Pisa, Italy as a classical example for this. You must have heard that this Leaning Tower of Pisa was leaning towards one side. Now, it has been replaced or erected to its vertical position very recently in 2001. Now, the function of the foundation is to transfer the load of the structure to the strata on which it is resting, and mostly it is the geological strata that consist of either soil or rock. Now, in order to design, there are certain important considerations. Now, one of the important consideration is the stability against shear failure. Now, when we say shear failure, we mean that the shear stresses which are there in the soil below the foundation, they are within permissible limits. So, they are related to the shear strength of the soil. And another important criteria is that the foundation must not settle beyond tolerable limits to damage the structure. Now, for different type of structures and for different type of soils, there are various permissible limits suggested by Indian Standard Code, and these limits are based on the performance of the structure. Let us say if a structure settles by more than a permissible value, then it may impart with the functioning of the structure. Like in the case of, let us say, buildings, if suppose that building foundation is resting on clay, and if the settlement of the structure is more than 75 millimeter or maybe 100 millimeter, which is prescribed by different IS code, and if due to that settlement there may be possibility of a cracking of the cracks appearing in the superstructure, and likewise there may be other inconveniences to the structure. So, this must not settle beyond a tolerable limit, and all these limits are given in different IS codes. Now, there are different type of foundations. Foundations may be considered as rigid foundation or flexible foundation. Foundations may be considered depending upon the depth of the foundation. So, here type of foundations that depends on the nature of the subsoil strata and the type of the superstructure. Broadly, we classify these foundations either as the shallow foundations or as the deep foundations. Now, in the shallow foundations it is an arrangement where structural loads are carried by soil or rock directly under the structure. Now, in most of the cases it has been found that the depth to width ratio is kept less than 1, and this is defined by various other researchers, and especially Tarjagi has given this criteria that if depth of the foundation to the width of the foundation is less than or equal to 1, it will be treated as the shallow foundation. Now, in case of shallow foundation, there are many other types, and some of them are like spread footings and mat foundation or the raft foundation. Now, spread footings, strip footings, continuous footings, rectangular footings, combined footings, all these come in the category of the shallow foundations as long as this depth to width ratio is less than 1. Now, in this figure, if you see that this is a foundation. Now, there is a column, this is a column foundation which is a spread foundation. This load is taken up by a larger area of the soil, and this foundation is in direct contact with the soil. Now, this total load imposed by this particular column foundation or one of the columns of the superstructure is it taken up by the soil which is below this, it may be soil or rock. Now, it is this depth, when we say depth, this is the depth of the foundation below the ground surface, this is the ground surface. In the case of mat foundation or raft foundation, when the area of the column footing or the spread footing is more than or equal to the loaded area, then in that case we go for the mat foundation or the raft foundation. Now, this is a combined foundation for many such columns, and the load acted by this column is taken up by the soil which is below the mat foundation. Another category is the deep foundations. Now, in the deep foundations we define the deep foundations as the members which carry the loads to the firm soil. Now, in this case the depth of the foundation to the width of foundation is greater than 1. Normally, pile foundations and the drilled shaft foundations, well foundations and foundations for bridge piers etc., we in the category of the deep foundations. Now, this is one of the deep foundation in which we have different piles and a pile raft. Now, here pile raft, although it is shown above the ground surface, but in most of the cases that this pile raft also is below the ground surface. Now, in this particular case, if you can see that these are the structural members which are called piles. Piles may be of different material. So, these materials are this material which is transferring the load from the superstructure to the subsoil, that is actually the member, and this member is that foundation. Now, the resistance is offered by the skin friction between the member and the soil and the end bearing of the pile tip. So, in the case of shallow foundations, like in this case the complete load is resisted by this particular in the bearing, whereas in the case of pile foundation it is resisted by the end bearing as well as the friction between the soil and the member. Another example in this case is the drilled shaft foundations, for it is used maybe for the bridge pier and for other structures. Now, the important criteria which we have seen that the foundation must not fail in shear, and that criteria is for this foundation which is the stability against shear failure. Now, it has been found that the factor of safety in the case of shallow foundation is always kept in such a way that the foundation does not fail in shear. Now, mostly the failure takes place, or when we say failure we mean the failure due to the excessive settlement and especially the differential settlement. We will have to keep this differential settlement within permissible limits, because this differential settlement is more dangerous to the stability of the structure. Now, in order to find out the bearing capacity or the load carrying capacity of the foundation from shear failure criteria, which we call it as the ultimate bearing capacity of foundation, there are many theories which were given by various researchers. For that, let us take an example of a foundation which is resting on soil. So, this is the foundation which is resting on soil, and here the load acting on the foundation is this load intensity Q and the width of the foundation is B. Now, when we apply the load, when we keep on increasing the load, there is settlement of this particular foundation, settlement of the foundation due to the compression of the soil, which is this soil strata. Now, when you increase the load per unit area, that is the pressure which is exerted by the foundation. Now, you will get the response, load intensity settlement response like this. In this, on this axis, this load per unit area is plotted, and here this settlement of the foundation is plotted. Now, you will find that with the increase in load, there is increase in settlement, and a condition reaches beyond which there is no increase in the load, but there is sudden drop of the stress taken. This type of failure we call it as the general shear type of failure. Now, in the another case where you will find that there is no clear cut failure, but the stress keeps on increasing and there is no clear cut failure, and the settlement and corresponding strains are very excessive strain. Now, we classify these two as the general shear failure and the local shear failure cases. Now, so these failures, one is general shear failure, the another is local shear failure, and the third category, which is intermediate between the local shear failure and the general shear failure, is the punching shear failure. Now, in the case of general shear failure, the situation is like this: you have this soil mass, and on this soil mass is resting a foundation of width V, and this is the load, ultimate load or the bearing capacity of the soil, that is Qu. Original ground surface is shown here. Now, with the increase in load, there is settlement of the structure, and you will find there are three clear cut zones which are formed below the foundation. This zone we call it as the elastic zone, and zone 2 and zone 3, these are called as the plastic zone. Now, there is development of the clear cut development of these plastic zones, and you will find that there is upheaval type, bulging type of surface which is on the ground surface. This is the case of the general shear failure. So, in the case of general shear failure, a triangular wedge shaped zone of soil marked 1 is pushed into the soil, and which in turn it presses the zones marked 2 and 3 sideways and then upward. At the ultimate pressure, which we call it as the bearing capacity, ultimate bearing capacity of the soil passes into a state of plastic equilibrium, and the failure is taken by sliding. Now, such type of failure occurs in the case of sands and clays, with this dense, in the case of dense sand with relative density greater than 70, and in the case of stiff clays. Another type of failure, which is the local shear failure, you will find that these zones, plastic zones, are not clear cut defined, but they are subdued, and you will find that the bulging is very small as compared to the general shear failure. In the third type of failure, which is punching shear failure, you will find that there is no development of this bulging, and the zones are not clearly defined. Now, in the case of local shear failure, the triangular wedge shaped zone of soil marked 1 below the footing moves downwards, but unlike general shear failure, the slip surface and somewhere inside the soil these ends. However, some signs of soil bulging are yield, but are not as pronounced as in the case of general shear failure. Such type of failure occurs in the loose to medium sand with relative density 35 to 70%, and in the case of soft clays. The third type of failure, which we call it as the punching shear failure, in the punching shear failure, the foundations penetrate into the soil without any bulging on the surface. The failure surface never reaches the top surface or the sand surface. Now, this occurs in the case of relatively loose sands with relative density less than 35%. On the basis of the model study, this is a relationship shown here between relative density of the sand and the relative depth of the foundation in terms of df by ratio. Now, you will find that for this case there are different zones in which you will find general shear failure, local shear failure, and punching shear failure. For example, let us say your depth to width ratio is equal to 1, and corresponding to that, this is the point below this it will be local shear failure, and above this it will be general shear failure. That will depend on what is the relative density of the sand, how stiff or how dense the stratum is. Now, in nutshell we can say that in the case of stiff clays and dense sand, normally we get general shear failure, and in the case of loose sand and dense clay, dense sand and loose or soft clay, we get the local shear failure. So, on the basis of that, in between we can get the intermediate. Now, these values are also defined as, if when we say dense sand, if angle of shearing resistance of the sand is greater than 36 degrees, you will get general shear failure, and if the angle of shearing resistance of sand is less than 28 degrees, then we call it as the local shear failure, and in between it is the intermediate failure. Now, there are many equations or the theories developed to determine the ultimate bearing capacity of the soil. Now, here we say ultimate bearing capacity is that pressure at which the soil can take up before failure. Now, here the rest of the terms related to ultimate bearing capacity I will discuss in the next lecture, but as far as the Terzaghi's ultimate bearing capacity equation is concerned, this Terzaghi equation is based on the Prandtl theory, which was postulated for the soft metals. Now, there are some assumptions which are made in the case of ultimate bearing capacity given by Terzaghi. Very first assumption is that he has considered the case of a strip footing. Now, when we say strip footing, in the strip footing the length dimension is far greater than the width of the footing, and we say when L by B ratio is greater than 5, we call it as a strip footing. Now, this particular equation has been postulated, or this theory has been postulated only for the shallow foundations, and we say that when depth to width ratio is less than or equal to 1, that is the shallow foundation. The third assumption which is taken into account is the weight of the soil of the base of the footing may be replaced by a uniform surcharge. Now, all the foundations you will find that they are placed at a depth below the ground surface, but here that depth, the effect of that depth is taken into account only by a surcharge given by Q equal to gamma into dF. Now, this gamma is the unit weight of the soil. Now, it means the resistance offered by the soil which is above this depth d is not taken into account, and that is that's why it is the shallow foundation. Another assumption is that footing base is rough. So, when footing base is rough, there is a formation of an elastic wedge below the foundation, and that wedge also penetrates into the soil along with the foundation. So, the case of only the general shear failure is considered, in which all the failure zones are clear cut developed, and there is bulging of the soil on the surface of the footing at the level of. Now, this is a definition sketch. You will find there is a footing column, this strip footing of width b, and it is resting at a depth dF below the ground surface. The effect of this depth is taken into account by this surcharge Q0, that is equal to gamma dF, and the level of the foundation is shown by this line, and these arrows are showing that surcharge. Now, there are formation of different wedges, wedge number 1, wedge number 2 and wedge number 3 on both the sides. Now, the inclination, this footing is considered as rough. You will find that this is a triangular wedge, which we call it as the elastic wedge, which also penetrate along with the foundation, and it pushes the soil, and there are formation of these plastic zones. The second zone, it is the plastic zone. This is the radial shear zone. Failure zone, failure surface you can see from here is given by IDF on this side, another failure surface is IEG on this side. Now, from here to here it is the radial shear zone, which is marked as zone 2, and then we have another straight line EG, that is marked as a straight line which is inclined at 45 minus 5/2. Now, here the inclination of different boundaries are also shown. This boundary B J is inclined at an angle phi with the horizontal, whereas boundary G E and F D and B D and A E, they are inclined at 45 minus 5/2. And this soil wedge is acted upon by the forces like C and PP, which is nothing but the passive earth pressure. Now, in this particular case, passive earth pressure conditions develop, and if you see the free body diagram of this wedge itself, you will find that there is weight of the wedge, the sides are inclined at phi, and you have this load intensity Q, which is the ultimate bearing capacity of the soil, and it is acted upon, the sides are acted upon by forces C and PP like this. So, here zone 1 is the wedge ABJ, which is the elastic zone, the sides are inclined at phi. Zone 2 is wedge AJE and BJD, these are the radial shear zones, in which all the radial lines starts from the edge of the footing. Zone 3 is the wedge AEG and BDF, these are the Rankine's passive zone. You must have learnt Rankine earth pressure theory, that is applied here. Then JD and JE are the arc of logarithmic spirals, which given by R equal to R0 e to the power theta into tan phi. So, these spirals are also function of the strength parameter phi of the soil, and DF and EG are the straight lines. So, this is the geometry of the wedge. Now, let us imagine that AJ and BJ are two walls that are pushing the soil wedge AD, EG and BJ DF respectively to cause passive earth pressure condition. So, when this soil is pushed by this particular wedge, now passive earth pressure conditions are developed here, and because of pushing of this, these shear zones are developed and soil is pushed like this, and you will get a bulging somewhere here, because in this particular case we are considering the effect of this. So, the bulging will be considered somewhere here. Then this PP, now here this angle of this wedge is equal to phi. So, this is the passive earth pressure condition, passive pressure. Now, this passive pressure will be inclined at an angle delta, that is the angle of friction between this material and this material. In this particular case, both the materials are soil. So, this will be taken as the angle of wall friction, that will delta, that will be equal to phi, and hence this PP will be perpendicular, means it will be acting in a direction of the weight. So, it is acting in the vertical direction, which will be inclined at delta with the normal to AJ. So, in this particular case, this delta will be equal to phi, where delta is the angle of wall friction. Here these walls are made up of soil. So, there is soil to soil contact, delta will be equal to phi. Now, as AJ and BJ are inclined at phi to horizontal, that is why PP should be vertical. Now, what we will have to do? We will have to consider the equilibrium of ABJ wedge per unit length. Now, when we consider static equilibrium, now here you will find that we are not considering moment equilibrium, although the errors involved may be very small and which can be neglected, but in this particular case it should be remembered that we do not consider moment equilibrium of the wedge. Now, the force which is acting downward will be equal to the force which is acting upward. Now, here the downward force will be due to the ultimate bearing capacity of the soil, which is acting per unit length on the width of the foundation, and the weight vector which is acting downward, the component of the cohesion which is acting on the side walls of the wedge, its component in the vertical direction, and then the pressure which is acting on the passive earth pressure or the force due to passive earth pressure which is acting in the vertical direction. Now, here this will be here I have considered this B as the half of the width. So, just for the simplification. So, this is equal to q u into 2 b, where B is equal to 2 b acting vertical downward, this per unit. So, this is multiplied by unity. Here weight vector, this is acting vertically downward, the component in the vertical direction and the vertical component here. So, for static equilibrium, these vertical forces are equated. Now, here W is the weight of the soil wedge ABJ, which can be determined by the geometry. Now, if B is the width and B is the half of the width, then the weight will be equal to the area of the triangle multiplied by 1 multiplied by unit weight. So, which comes out to be equal to gamma B square tan phi. Now, C is the cohesive force which is acting along each face AJ and BJ. So, we will have 2 C, there are 2 faces, and those will be equal to the unit cohesion times the length of each face. So, length of the so it will come out to be equal to C into B upon C cos of C into B upon cos of phi. So, if you substitute these in equation 1, you will find this will become equal to 2 B into q u, that will be equal to 2 p p plus 2 b c tan of phi minus gamma B square tan of phi. Now, this can also be written as q u equal to p b upon B plus c tan of phi minus gamma B upon 2 tan of phi. This is equation number 3. Now, the passive pressure in the above equation is the sum of the contribution of the weight of the soil, cohesion and surcharge. Now, what we can do? We can separate all these 3 by considering only one and then others 2 by neglecting others 2 or keeping those 2 as value 0. Now, here in this particular figure, now this is shown the contribution of the soil weight. Soil weight is because of the unit weight of the soil. Now, here this is that face of the elastic wedge. Now, here this is acting as a wall and it is pushing here. So, there is a passive resistance which is developed here, and that passive force that will be dependent on what is the depth of this particular point J below the ground surface, and the pressure distribution will be triangular. So, here if h is the h will be the height of this, that h will be given by B into tan of phi, where B is half of the width, and this will be acting at a height that is equal to h by 3. We have already seen that this particular force will be acting at an angle phi or delta with the normal to the this particular plane JB. So, here this pressure distribution is triangular, this inclination of wedge is phi, here this will also be equal to phi, and it will be given by half gamma h square into k gamma, where k gamma is the passive earth pressure coefficient which can be determined by Rankine theory. Similar to this, the contribution of the cohesion. Now, cohesion will be considered uniform all along this side, that is JB, and hence the contribution will be given by C into H into Kc, and this will be acting at a height h by 2, whereas in the earlier slide you must have seen it is acting as h by 3. You can find it out from the Rankine earth pressure theory. Similar to the contribution of surcharge Q0, that is gamma into dF. Now, that surcharge pressure distribution is like this, it will be uniform throughout the height of the or the length of the wall. Now, here this will again be acting at a height of h by 2, and the magnitude will be equal to q into h into kq, where kq is the coefficient due to this surcharge. Now, thus we can write that equation number 3 as P p equal to 0.5 gamma B tan square phi k gamma plus C B tan square k c q 0 B tan of phi k q, where k gamma, k c, k q are the earth pressure coefficients, and these earth pressure coefficients are function of angle of shearing resistance of the soil. Now, when you combine this equation 3 and 4, we obtain this in the form q u equal to C n c plus q 0 gamma Q0 NQ plus 0.5 gamma V N gamma. Now, these NC, NQ and N gamma, these are the bearing capacity factors, and these bearing capacity factors are function of the strength parameter phi, where NC is given by 10 phi Kc plus 1, NQ is given by Kq 10 phi, N gamma is given by 0.5 10 phi, K gamma 10 phi minus 1. The term NC, NQ, N gamma are respectively the contributions of cohesion, surcharge and unit weight of soil to the ultimate load bearing capacity. It is extremely tedious to determine this value Ke, Kq and K gamma. So, what Tarzaghi has done, Tarzaghi has given the following equation factors on the basis of the semi empirical theories which we have developed, which he has developed, and these are given by these equations like NQ equal to A square upon 2 cos square 45 plus 5 by 2, where A is equal to E eta tan of phi, eta is given by 3 by 4 pi minus 5 by 2, and NC is equal to NQ minus 1 into cot of phi, and N gamma equal to half tan of phi K gamma upon cos square phi minus 1. Now, Tarzaghi bearing capacity factors can be determined from these equations, and these are tabulated in this chart. There are various values of phi from 0 to 50 degrees, and corresponding to that we have NC, we have NQ, we have N gamma. Now, these values are, for example, for phi equal to 0 5.7, NQ equal to 1 and N gamma equal to 0. Similarly, for 50 degrees, this is NC equal to 347.5, 415.1 and 1153.0. Now, depending upon the angle of shearing resistance, this angle of shearing resistance we can find out from different tests, and then we can pick different values of NC, NQ, N gamma and substitute in the Tarzaghi bearing capacity equation. We will find the ultimate bearing capacity of the soil. Now, Tarzaghi actually has used an approximate method to determine ultimate bearing capacity Q. The principles of approximation follows: if C equal to 0 and surcharge equal to 0, that is depth equal to 0, we will have Q that will be equal to Q gamma, the component of only the weight. Similarly, when gamma equal to 0 means we assume this soil to be weightless, and Q equal to 0, then Q equal to QC, that will be the component of only the cohesion. Similarly, when gamma equal to 0 and C equal to 0, we have Qu that will be given by Qq, that will be the component of NQ only, and that is due to only the surcharge. So, I am sorry, this is equal to Q and Q here. Then by the method of superposition, the effect of when the effects of unit weight of soil, cohesion and surcharge are considered, then we are left with this equation Q equal to QC plus QQ plus Q gamma, that is given by CNC plus QNQ plus 0.5 gamma B N gamma, the same equation which we have got here as the bearing capacity equation. Now, in the case of the local shear failure, here local shear failure we say that when phi is less than 28 degrees, in that case we take these parameters as C dash, that is 2/3 of C, and 10 phi dash, that is equal to 2/3 of 10 phi, and C dash and phi dash we determine, and corresponding to the C dash and phi dash we find out the corresponding bearing capacity factors, and then we find out the ultimate bearing capacity theory. Thank you.
Thank you.